All right, so following up with the previous video that showed to you on intersection of planes, I'm going to repeat one of the examples that I did in that video, except this time I'm going to be using something called a matrix. Now, matrices are very helpful little systems to be able to solve algebraic systems without maybe having to do all the algebraic work that you're familiar with from your previous courses and what I've shown in the previous video. So, but matrices need to be set up very carefully and you have to be organized, much like everything else in math. So the equations are set up in a format I can use nicely. So we have x, y, and z and your constants. Okay, and they're all equal to 0. So that's important to set them all up in a proper manner. So I'll show you what a matrix looks like. So what we do is we take the values, we use these large squared off brackets, and we take the coefficients of your x, and it's important to identify your columns. That's important for your matrices. Then we identify the y coefficients, and now notice here is a 0, 1, and 1, and then finally the z. So each column represents a particular variable. So the x coefficients, the y, and the z. You want to maintain consistency too, so you know which one is which. And then sometimes the matrices are drawn with this line if you have some constants or coefficients. Now, you might be wondering, why is this -11, -4, and 3? Well, part of the system with matrices, I'll just draw it out with the first one here, is that you have this type of algebraic look. So 3x plus 0y, and then plus 1z, for this particular equation anyways, equals -11. So that is the proper format to be used in this matrix. And that's what that big line is indicating. It's kind of like representing the equal sign. Okay, so that's important to set that up. So each one of these equations have to be set up in this manner. So you're bringing the constant to the other side and then setting it up this way with this big large line that represents the equal sign. Okay. Now with the matrix, the goal for your matrix is to kind of look like this, and I'll explain why. You want zeros in these locations. So here's basically what's going to happen. So if every column represents a particular variable, then this will be the x column. So 1x will equal some number. And then the next column, you'll have y, 1y equals a number. And then in the third column, 1z equals another number. So this will allow you to solve your system, much like we did in the previous one. So if we're looking for a point of intersection, we can get an x, a y, and a z equaling different numbers. So how do you get to this goal? Well, that is using the same types of techniques that you've used in the past in terms of elimination, but in a slightly more different way, and it's written in a certain different way. Okay, so the way you go about doing this is essentially you want to try to obtain a 0 here and a 0 there and a 0 here. So you want to maintain these ones through here. Now, luckily enough, we already have ones here. So question is, how do I make this number 0? How do I get this number 0? Well, you tackle it the same way you would elimination, but you're just using the constants. You do not use the algebra itself. So let's see how this works. So row 1 stays the same. So I'll follow this along with the pen here. So row 1 stays the same. Now, how did row 2 change? Row 2 changed because I wanted a 0 here. Now, how do I get a 0 here? Well, it's much like elimination. If I'm going to use row 1 to eliminate this 2, I want these numbers to be the same. So I have to multiply the 3 by a 2 and the 2 by a 3, and then subtract, because that will give me 6 take away 6, giving me a 0. I don't care what the other values are, but I need the 0 here, okay? Leaving the third row alone. So you just work with pairs at a time. You don't try to get too complicated and do too much all at once, all right? Okay, so and now I have a 0 here, so my goal has been met as far as this part is concerned, and I continue the process. So now I need to get a 0 here, so I'm going to leave the first row alone, Second row has now been changed. I'm going to leave that alone. But how do I get the 0 here? Well, if I'm going to be using row 1 again, I need these coefficients to be the same. So I need to multiply this third row by 3, leaving the first row alone, and then subtract. And then again, whatever values I get here and here, doesn't matter. But again, that's the elimination process. Okay. And then I'm going to continue this process. So I'm going to leave row 1 alone. Row 2 has the 0 where I want it to be. Row 3 has the 0 where I want it to be, but I want another 0 here. Okay, so again, remember what this goal is. I want to try and get these little zeros down in here and eventually, hopefully, get some zeros up here. Although it's better to work with the bottom sections here. So again, using the numbers, I'm trying to get rid of this -3 now. Now notice the only thing I have to do is subtract row 2 and row 3 to get that to occur. So I'm going to leave row 2 alone, subtract row 2 and row 3, and write the coefficients here. Now, I don't necessarily need to continue and get the ones all the way across. This is more of a university type of concept. I'm not going to get into any of the language. So you could technically stop there. Now, why? Because this is in the Z column. So 7Z must be equal to 10. Can I get an answer for Z? Of course I can. Now, once I have that answer for Z, this is going to give me an equation of -3y plus 5z equals -10. So could I solve for y? Absolutely. Or I could continue what we refer to as row reducing. That's what this concept that we've been looking at. And try to obtain a 0 here and a 0 there, and then put 1s down here. So you have choices when it comes to matrices in terms of what the nature of the problem is and how to solve it. All right. So this is just a small little sample of how a matrix can shorten some of the work, perhaps. Like I said, you can even avoid some of this algebra here by continuing this process with the matrix and working with it to try and obtain a 0 here. So you could use the second row and multiply the first row by 5 and then subtract. And then you need to divide each one of these rows by those coefficients to try and get those 1s in there and then get it to look like this. Okay. Either way, you'll wind up getting the same result as in the previous example in the previous video. So whether you want to use the matrices to get a complete goal of what I talked about earlier, or you can stop at a certain point where you can work algebraically, completely up to you. Okay, so there's lots of different ways for solving techniques. But like I said, matrices are usually covered in university concepts, but I thought I'd just add this in here for those of you that would be interested.